Okay, so the last section of chapter 20 has to do with nuclear binding energy. This is the energy that goes into holding a nucleus together. You may recall that protons are mutually repulsive toward each other. There's this kind of difficult to understand thing called the strong nuclear force, which holds protons and neutrons together strongly enough to hold a nucleus together stably. And so the energy that is required to hold all those protons together into a nucleus is an incredible amount of energy. And we're going to see that in a similar way to how we analyzed our fission reactions and alpha decay reaction earlier. That is by looking at the observed masses of everything that makes up a nucleus. So if you consider a helium nucleus, helium's got 2 protons and 2 neutrons. Again, we can precisely measure the mass of helium, the mass of the proton, the mass of a neutron, and they don't quite add up. Helium is less than the sum of its parts. So take the mass of helium and compare it to 2 times the mass of the proton and 2 times the mass of the neutron, and you find out that you are missing 0.03037 grams per mole. That's not a small amount. That's about 10 times the mass that was lost through the uranium alpha decay process. This is called the mass defect. The mass defect is the amount by which the mass of a nucleus is less than the sum of its parts. And again, we can convert this to kilograms, right? So 0.0000, we'll add 3 zeros, 3037 kilograms per mole, and multiply that by C squared. That will give us an energy. And in fact, I don't have the energy for that. But I can tell you it'll be on the order of 4 times 10 to the 7th kilojoules per mole. And so what energy does that represent? The mass defect is caused by the nuclear binding energy. So that is the energy that is holding the nucleus together. And so just like chemical reactions involve breaking some bonds and forming some new bonds, and we compare the relative strengths of those bonds to figure out whether it's exo or endothermic and by how much. For nuclear reactions, we're basically comparing the binding energies of the products to the binding energies of the reactants and seeing how much energy gets released. So a more stable nucleus is going to have a higher binding energy, and its mass therefore will be smaller, and it will release a lot of energy if that's a product of a reaction. So if you were to, and I'm a little disappointed, your textbook doesn't have this figure. Most textbooks do, so I'm just going to sketch it for you. And so if I were to take as my x-axis the atomic number, and then as my y-axis I take the binding energy divided by the number, I'll just call it the mass number, right? The mass number is the number of nucleons, or the number of protons and neutrons. Then this is going to tell you, about how stable the nucleus is. The highest binding energy elements are going to be the most stable. And what you get is a curve that looks roughly like this. Okay, so an element like hydrogen has 0 binding energy because hydrogen is literally just a proton. And then deuterium or tritium will have some binding energy. Helium will have some more, so I'll just write some in here. Helium and lithium and carbon and oxygen and neon. Anyway, as you get larger and larger atoms, the binding energy increases. And this is why within the cores of stars, fusing to larger and larger atoms is able to release energy and continue to fuel that star. Well, it reaches a maximum at iron. Iron has the greatest nuclear stability of all the known elements. And so smaller atoms will tend to fuse. So this is where fusion occurs, provided you have high enough temperatures and pressures, like say in the core of a supermassive star. And then everything over here will achieve greater stability by breaking apart and forming smaller nuclides. So everything that's really big is on this downward slope. You know, here would be uranium, for example. And for uranium to release energy, it needs to break apart into two smaller elements that are a little bit higher up on this binding energy chart. So anyway, iron is really special in this way. Within a star, you're going to see production of all the elements up until iron in sort of steady processes that occur in the core of that star. And all the elements beyond iron are produced in non-equilibrium conditions like a supernova, and they're ultimately not stable compared to iron, and that's why they will undergo fission to reduce their atomic number and approach this maximum in binding energy per nucleon. Okay, and that's it for chapter 20.